Okay, before we move on to some ideas about transformations, I do want to point out that in your book you do have the information that we just discussed all in a nice box here for a exponential function. Okay, talks about the same analysis that we just mentioned in our notes a few minutes ago, so refer to this when needed. Okay, and ultimately if we understand the behavior of a general exponential function, as we discussed a minute ago, okay, then we can talk about transformations. Okay, and since we know a lot about transformations already, okay, most of what we're going to look at today should be pretty much a review regarding transformations. So let's talk about the 2 to the x function. We saw what the graph of that looked like. Okay, so ultimately the question is, what's it going to look like if we graph 2 to the x minus 1? Well, if we replace x with x minus 1, okay, in our other types of functions, that caused a shift of 1 to the right. So should that be any different for this type of function? Absolutely not. Okay, all the same rules are going to apply here that applied in the past. So therefore this should be the same function but shifted 1 to the right. Okay, we've already discussed this one. If I were to put a negative x instead of x, that's going to create a reflection over the y-axis, which we saw that did because we know that this is the same as 1/2 to the x. Okay, and then ultimately multiplying the whole thing by 3 is going to create a vertical stretch, just like it did on our other types of problems, mainly polynomials that we've dealt with. Okay, so just a quick look at some pictures here. If we were to graph this 2 to the x minus 1 function, as we can see, they did graph it. They moved the points over 1 to the right. Okay, still the exact same behavior. Okay, still have the same y = 0 asymptote going to the left. Okay, the whole thing though is just shifted 1 to the right. And as we discussed earlier, we're going to have 2 to the negative x is going to create a reflection over the y-axis. Okay, it can become a decay function, as we mentioned. And then finally, the stretch is going to take all the y-coordinates of the original and multiply them by 3. That's going to create a vertical stretch. So we should see that it grows actually faster than the 2 to the x function, if you will. Okay. All right, so again, all of our transformations are going to have the same rules that we had prior. Now, one of the bases that we're going to see quite often and use in a lot of application problems is this base e. Okay, e is a number that we've met before in algebra and algebra 2. Okay, it's a irrational number, kind of like pi. The decimal is 2.71, goes on forever, no repeating, no terminating. It's an irrational number. Okay, and ultimately what it boils down to is that this number e is actually the answer to the limit as x approaches infinity for this special function. Okay, and what it boils down to is this special function comes up in a lot of applications of science and finance and so on. Okay, but ultimately if we were to graph this function right here and look at what's going on at infinity, okay, it would go to 2.71 blah blah blah. Okay, so the limit of that expression is e, and like I said, there's some applications that particular function come into play when we deal with exponential situations. Okay, so ultimately, okay, what it boils down to is that any exponential function can be rewritten in the form a times e to the kx. Okay, so we can take any exponential function that was given, okay, and we can transform it into this form a times e to the kx. Okay, for an appropriately chosen value of k. Okay, and ultimately the same rules apply here. If we have e to a positive coefficient on x, it's going to be a growth function. And if k is negative, if we have e to the negative x, okay, of some sort, negative 2x, negative 5x, negative x, that's going to be also a decay function. It's going to have the same rules we had for any general exponential function. Okay. All right, we do have a couple of pictures here. When we have, again, k greater than 0, we have a growth function, just an illustration of the properties that we just looked at a minute ago. Notice that we still go through 0, 1 in both cases, because if we put a 0 in for x, we're going to get e to the 0, which is 1. Okay. All right. And also, transforming works the same way, same rules. So we already know what's going to happen with this one. It's going to be the e to the x function, but move 2 to the left, plus 2. So when we're opposite when we're in the x direction. If I were to put a negative sign out in front, that's going to take my e function and flip it over the x-axis this time. So we'd flip it over the x-axis. If I have e to the x minus 1, that's going to take the whole thing and move it down 1. So again, all the same transformation rules apply, which is nice. Okay, that's never going to change. No matter what kind of function we're dealing with, the transformation rules do not change. Okay, which is very convenient. We don't have to learn a whole new set of rules. Okay. All right. Now, before we look at the other type of function for today, I do want to point out also that on page 281, they have the analysis of one of our parent functions. Remember, one of our parent functions was y equals e to the x. Okay, they have the analysis here, all the pertinent information about that. Okay, with all that information, we can handle the analysis of any other transform exponential function. But again, I wanted to point out that that information is right there on page 281 in your book. Okay. Okay. Now, we do have one other type of function we're going to look at today that's very similar to an exponential function, and that's what we call a logistic growth function. Okay. I'm going to go ahead and go back to the notes here. When we have a logistic growth function, okay, the general form can look like one of these two forms. It can be of the form c over 1 plus a times b to the x, or it could be of the form c over 1 plus a times e to the negative kx. Okay, so both of these are what we call logistic growth functions. Okay. The only stipulations here are a, b, c, and k need to be constants, and they need to be positive. Okay, and the b value here needs to be less than 1. Okay, so if in this case, if it was written in this form, the b would have to be less than 1. Okay. And ultimately, they all have to be positive. And one other point here, the c is the limit to growth. Okay, this limit to growth means that there's going to be a horizontal asymptote for this function, and it's going to be at y equals c. Okay, so ultimately that translates to a horizontal asymptote at y equals c. Okay, and let's go ahead and take a look at a problem that involves a logistic function. Okay. You got to follow with me. I'm on page 287 now. I want to look at number 49. I'm going to go ahead and type that into my calculator because I want to see what that picture looks like. So we have 5 on top, and on the bottom we have 1 plus 4 e to the negative 2x. I'm going to do a standard window here and see what we see. Right. And as you can see, it was really close to the y-axis here, or x-axis I should say. It goes up kind of like an exponential function, but instead of continuing to go up forever, this type of function essentially levels off again. Okay, and that's why in this case we're going to have two horizontal asymptotes, one going to the left at y equals 0, one going to the right at y equals, remember what I said earlier? C is where we're going to have the horizontal asymptote on the right side, so it would be y equals 5. We could check that with our table as well and see that those values as we go to the right are getting closer to 5. But that right there is going to be the general shape of a logistic equation. Okay, and sometimes that when populations grow, this is where we generally use this, sometimes populations grow exponentially for a while, okay, but then at some point they taper off. Okay, and if they taper off, yeah, that's generally due to maybe how much food there is in the area, because ultimately if we just continued to grow exponentially, would there be enough food to feed everybody? Okay, so eventually populations tend to taper off, and so populations a lot of times are modeled by logistic functions because there's going to be a certain amount of people that there's going to be ultimately a maximum amount of people they're going to be, and we generally in science call that the carrying capacity. So whatever environment we're working in, there's going to be some kind of carrying capacity, okay, and that ultimately tells us how many people or bacteria or whatever animals we're dealing with, okay, that are going to be the most. Okay, all right. So that's a general picture. If you turn the page with me to 287, it says on number 55 on the top left-hand side, tells us that the 20th century U.S. Census data, the population of Ohio, can be modeled by a logistic equation. I'm going to go ahead and put that in my calculator. So it says 29, or no, I got that wrong. It says 12.79 on top. And then at the bottom, it's 1 plus 2.402. And then it's e to the negative 0.0309x. So this is the equation that models that. I can see that 12.79 is my C value here. So if I want to see this, I'm going to need to change my window, make it a little bit bigger. I'm going to go up to 15, let's say, and then I'm going to do my zoom 6. And we can see that as it goes through that area, that it hasn't quite gone exponential. Right? Okay, it hasn't gotten up to the 12.79 that we expect. That's going to happen down the road here to the right, if you will. But what it says here that says that we want to go based on this model. Okay, when was the Ohio population 10 million? So remember, the y-coordinates here are the populations. So essentially, we just want to know what's the solution to that stuff equaling 10. Okay, because again, this is measured in millions, and we want to know when it's equal to 10 million. So if we were to graph it again, okay, we can see that it's nowhere in this window. We're going to have to move off to the right to see if we can find the intersection between these two. We're not going to solve this with an algebra approach at this point. We're just going to solve it with a graphing approach. So if I change my window, let's say we go to 100 years down the road and see what happens. So here's my logistic function, creeping up there by 12.79, starting to taper off. Looks like we do hit 10 in that window. So if we go ahead and use our intersection command, we're at 69.67, so approximately 70 years. And in that problem, I told you that it's years since 1900. So if we round that to the nearest year, we'd say about 1970 would be when it gets to 10 million. Okay. All right, so you'll notice the kind of the common theme that we've talked about here today is that most of the problems and the things that we've talked about are really nothing different than we've already done. Okay. We are just using a different type of function. We're using exponential functions and logistic functions, and essentially answering the same types of questions that we have been doing with polynomials, etc. Okay?